Ladies and gentlemen, welcome to the Great Hall here at the University of Sydney. I am not Brian Schmidt. My name is Chris Stewart. I am the manager of the International Science School, which is currently running here at the University of Sydney over these couple of weeks of the school holidays. We have 140 high school students, some of whom are here in the audience tonight. And the International Science School is co-hosting this public talk tonight in conjunction with Sydney Ideas. So welcome. Before we begin the proceedings, I would like to acknowledge and pay respect to the traditional owners of the land on which we meet, the Gadigal people of the Eora Nation. It is upon their ancestral lands that the University of Sydney is built. And as we share our own knowledge, teaching, learning and research practices within this university, may we also pay respect to the knowledge embedded forever within the Aboriginal custodianship of country. So as I said, welcome to the University of Sydney. We're going to have a very interesting evening tonight. The formal part of this evening's proceedings is a presentation by Professor Schmidt, to be followed by question and answer. And as you came in, you may have noticed that we have two microphones up the aisle. I'll be directing you to those microphones later to ask your questions, rather than just shouting them out from the audience. We'll direct you over to the microphones, and I will be shepherding those questions through to Professor Schmidt as we go. Could I also ask everyone to silence their mobile phones at this point? I've just turned mine off because there's nothing more embarrassing than having that go off as you're asking other people to silence their mobile phones. And I also need to point out that this event is being recorded. You'll notice cameras on either side of the room. We're videoing this, and it will be put up on the university's website as a video webcast for viewing later. So if you want to see yourself in the video, make sure that you pop up at appropriate times. And if you don't want to see yourself on the video, then just hunch down a little bit further in your seats. But it's now my great pleasure to hand over to Professor Trevor Hambley, the Dean of the Faculty of Science, to make some welcomes and introductions. Professor Hambley.
Thanks, Chris. Good evening, ladies and gentlemen, and welcome. I'm both honoured and delighted to have been given the opportunity to introduce our speaker this evening, Nobel laureate, Professor Brian Schmidt, laureate fellow at the Australian National University and Mount Stromlo Observatory. Professor Schmidt was raised in Montana and Alaska and obtained his undergraduate and postgraduate degrees at the University of Arizona and Harvard University, respectively, completing his PhD in 1993. Very soon after that, in 1994, he and Nick Sundstedt led a team of 20 astronomers from around the world in a study using distant exploding stars to trace the expansion of the universe. Their discovery from this work, that the expansion of the universe is accelerating, was identified very quickly by Science magazine as the breakthrough of the year for 1998. Brian joined the staff in the middle of that project, the staff of ANU, in 1995, where he is now a distinguished professor and Australian Research Council Laureate Fellow, as I mentioned. Professor Schmidt was awarded the Malcolm McIntosh Prize and Harvard University's Bok Prize in 2000 and the Pawsey Medal in 2001. In 2006, he shared the Shaw Prize in Astronomy with Adam Rees and Cyril Perlmutter, and this is the same team that was awarded the Nobel Prize in 2011 for the discovery of the accelerating expansion of the universe. Professor Schmidt is continuing his studies of the universe and is leading the efforts to build a new telescope which will provide a digital map of the southern sky over all wavelengths from ultraviolet to infrared. Professor Schmidt is also a passionate promoter of science and maths education. And in fact, he just told me that this is going to be his 8th event today, having come up from, left Canberra at 4:30 this morning and done 6 events with Dr. Karl before appearing at the ISS and joining us this evening. And since winning the Nobel Prize, Professor Schmidt has contributed extraordinary amounts of his time and energy to putting the cases for scientific research and education to politicians, to the media and to the community. And for all of this, we are deeply grateful as a scientific community. These commitments and the other expectations that come with winning a Nobel Prize put a lot of expectations on Professor Schmidt, and therefore we're especially honoured and pleased that he's agreed to talk to us tonight. I invite him to the stage to give his talk, Exploring the Last Frontier, Australia's Pioneering Work in Astronomy. Professor Schmidt.
Thank you. right. Well, thank you very much. And so today I'm going to be running you through a story of the universe, which I'm going to tell from the perspective largely of Australia, because Australia is one of the world's great astronomy nations, and that is why I moved here at the end of 1994. And Sydney University, along with my own university, ANU, is really the heritage of a lot of that research. And we'll be talking about some of the things that we have collectively done in this country to understand things and talk a little bit about the past, a lot about the present and the future. And we can be justifiably proud of what we have learned here, and I think we often forget just how influential we can be on the world stage when we put our minds to it. So, let's go back to something which is not about Australia. Let's go back to the fundamentals of science and of astronomy. Astronomy is the second oldest profession, but the oldest science. So if we think back to Copernicus, Copernicus had an idea, and that idea was that the Earth is not the center of the universe. Now, ideas are good, but what makes an idea really good is to show that it predicts something, and that is the fundamental basis of science. It's taking an idea and predicting things. We think of it as being facts and figures. It's not. Nothing is a fact in science. Everything comes with uncertainty. So Copernicus had this idea of predicting how the planets moved across the sky. And that idea, turned out, didn't do any better than the Greeks' idea, which had the Earth at the center and everything going on circle upon circle upon circle. His idea had the advantage it was simple. Now, the way that Copernicus's idea became the reality we perceive today was that when we started looking at something like Jupiter shown up here, Galileo got to do the same, and Galileo invented something. He didn't invent, he improved the telescope. And so astronomy and science is based on ideas and observations require equipment. That's why you will always see scientists wanting more money to buy equipment, because if you've got the equipment, you can do things. And so Galileo was able to effectively invent the modern ideas behind science because he had the equipment to do so and to show people what the ideas, whether or not they were right or wrong. So what he did is he saw Jupiter or Saturn, and when he looked at Jupiter, for example, instead of looking as just a dot that traveled across the sky, it ended up looking like this. It was an orb. It was not a star. It was surrounded by 4 moons that orbited it. Very clearly, the Earth was not the center of this system. Instead, he recognized it very similar to being the Earth with its moon, but it meant immediately that Copernicus was right. The Earth was not the center of everything. It was much more sensible to put the sun at the center. Now, Galileo, it was an interesting guy. I've had the opportunity to give a lecture on the lectern he used to use in the room he used to do it in. That was fun. I'm not sure how much the Italians understood my English, but probably better than I understood their Italian. But I also got to see where Galileo was later imprisoned. And the reason he was imprisoned is because he really liked making telescopes for the rich people, including, for example, the Pope, and showing them with their own eyes that Jupiter looked like that, Copernicus was right, and the church was wrong. So anyway, he was put off to this terrible Tuscan village, a villa that had 6 rooms, 40 acres of vines out the back, looking on to Tuscany at the top of Arcetri, just outside of Florence. It was a prison, but a pretty nice one, as near as I could tell. So ideas become reality with observation. Now, if you go through and look at a modern-day thing, Einstein had an idea of how gravity works. That idea happened in 1915, where he did his theory of general relativity. And the idea there was a very simple one, which was based up mathematically on a simple premise that acceleration and going faster, that is, accelerating, were equivalent always. A small little thought that took him 8 years to solve. But the way it was figured out was by making observations, and observations in this case done by Sir Arthur Eddington, where he led an eclipse expedition and showed that the sun bent the light of background stars just like Einstein's theory predicted, and not like Newton's theory predicted. So the follow-up observations, which are actually regarded as being much better now, were actually done here in Australia in 1922 by 2 visiting American astronomers. But once again, Einstein became an instant celebrity at this point because from pure thought, he had this idea, not based on some observation. Rather, he had an idea that became reality through these observations of stars behind the sun when it was fully eclipsed. So our typical way of looking at the universe as astronomers is through telescopes. So let's just talk a little bit about a telescope. Our eye is the telescope we all are used to. It's a little tiny 5-millimeter telescope, and it serves us very well. But if we make telescopes bigger, we get a couple good things. We have larger telescopes, and they collect a lot more light, so we can see things that are fainter. But it turns out they greatly improve detail, and that's because of the nature that light is a wave, and wave effects, or what we call quantum mechanical effects, mean that when you use a little telescope to look at waves, it becomes blurry through what we call diffraction. And so larger telescopes are extremely useful to improve detail. The other thing that telescopes allow us to do is to put modern digital detectors behind them. Our eye is about the same sensitivity as a photographic plate. A photographic plate can be sat there and it can look at the sky for an hour, so it can see fainter. But modern digital detectors are almost 100 times more efficient than our eyes at collecting light. And so you can improve things by a factor of 100. That's like building a telescope 10 times bigger. And so that improvement has been one of the things that's allowed astronomy to do so much in the optical regime in the last 30 years. Unfortunately, we're up to almost 100% efficiency in our digital detectors. So we are never, unfortunately, ever going to get that gain again. So let's say we look at Saturn, for example. Now, when Galileo looked at Saturn, it didn't look like this. This is a picture from a space probe where he really just went up and took a picture up close and personal. So Galileo, when he looked at Saturn, it would have looked something like this. He described it as the planet with ears, because he didn't have a very good telescope. So it was later realized by Cassini and others that it had rings. But if you were to go and take a nice normal-sized telescope here in Sydney and go out, Saturn's up right now. It's kind of a reddish thing, almost straight overhead when we go out in an hour or two. It's going to look something like that. Now, the reason Saturn looks blurry is not because of your telescope, assuming you've bought a quasi-reasonable one. It's because Sydney is such a bad place to do astronomy. Why we don't build new telescopes at the Sydney Observatory anymore. And it's bad because, not because the sky is cloudy, although it is quite often here, but it's because of turbulence. The atmosphere is full of turbulence. And that turbulence distorts how stars look. And so if you were instead to go from Sydney, you were going to go, for example, up to Siding Spring Observatory near Coonabarabran, you can get to a place on top of a mountain that has a bit better or a bit less turbulence. Sky will look better. But still, that picture of Saturn isn't crash hot. What we like to do is to put telescopes on tops of mountains in deserts. Now, it turns out Australia has deserts. It sort of has mountains. As someone from Alaska, we have hills. And so Australia doesn't really have any place now to really put the best new big telescopes. They tend to go in the Atacama Desert, the driest place on Earth, that also happens to have 6,000-meter mountains coming right out of the ocean, or on Mauna Kea in the northern hemisphere, which is a volcano that comes out of the ocean and is effectively a desert up at 4,000 meters in height. And so if you were to look at a picture of Saturn there, it would look something like that. Now, one of the things we can do, here's a picture of what a star looks like if you take a movie of it from one of these telescopes. And you can see that it's moving all over the place, and that's what the turbulence does. But with modern technology, we can go through and effectively put a mirror that we can deform like a contact lens, and we move it as fast as the sky moves. And so you sort of correct the atmosphere 1,000 times a second. And that enables us to get Saturn to effectively look just like it would if we were up close and personal. To show you that technology, let's show it on not Saturn, but on Uranus. Here is a picture with the Keck telescope, the world's largest telescope. And you can see on the left, that's what an image looks like on a good clear night. And then you turn on this active correction. And suddenly you get a picture that is better than what you can get in space with the Hubble Space Telescope. So this technology is driving what we can do, and I'll show you this again and again and again. Technology drives what we can do, but we also drive technology. It is quite interesting that the adaptive optics systems right there that you've seen are now being used in trial ways to help improve how we do laser surgery on your eyes, because your eyes have turbulence in them, just like the atmosphere. And if you're going to go in and try to attach retinas or carve things out in the back of your eye to fix your eyes, if your laser is all moving around, you don't do a very good job. This allows you to do precise work. So it is funny to see how things come back. In the same way, the digital detectors, which were developed by the military, astronomers are the ones who really use them. And so we made them become a commodity. And so that allowed huge advances to be made, which now then feed into the consumer market. And the great thing for us is once they get into the consumer market, these detectors, which we typically would spend millions of dollars on, become hundreds of dollars. And so we benefit from the technology as we advance it. So to make these adaptive optics work, we use lasers. Here is the Gemini telescope, and the laser coming out of it is a little more complicated than you might think. This is a modern 5-laser system, and so that gives you these fake stars that you're going to use to figure out what the atmosphere is doing and to correct. This is a telescope Australia is a partner in, and it is a system which Australia has helped develop. We have a very strong team up at Mount Stromlo that is going through at what we call the Astronomy Instrumentation Center, you can see up here. And Mount Stromlo has been actively doing astronomy in the research sense since the 1920s. There we are, one of the old buildings built in exactly the same style by the same architect as Old Parliament House, if you look at it. Now, that building was largely destroyed in 2003, but it has been rebuilt, and I can honestly say it is a lot better than the original. But it looks the same. Now, Australia doesn't just do optical astronomy. It does radio astronomy. And a lot of that radio astronomy was developed here at the University of Sydney. Up here, we see some of the early pioneers of radio astronomy. And I'm going to particularly mention the woman, Ruby Payne Scott, who is one of the iconic astronomers of Australia, but through misfortune of being a woman in a time when women were not really allowed to do things, her legacy has not been fully realized. And I think it's important for us to appreciate she is really the father of modern radio astronomy, except for she's the mother of it. And so what she did, along with the other two people you see there, was able to use radar dishes after World War II finished to start looking at the sky. And they immediately found that there was things like the sun emitted radio waves. And they were able to use the technique and develop the technique that everyone in the world uses now, which we call interferometry. This is where you use the properties of waves. You put waves together to get more information, sort of like a Vernier scale or a slide rule for people who can remember back that far. This is the place where you can use the fact that waves add and subtract, and I'll show you that in just a second. So out just south here of Sydney, there's a nice little memorial you can go down and look at. They could go through and they could look at things with these big antennas. And the idea was this. You would go through and you would look at, let's say, the sun. And when you made those observations of the sun, the light would come directly from the sun, but it could also, radio waves in this case, directly from the sun, but then it would also bounce off the ocean back up to the antenna. And this path was a little different than that path, which means light as a wave, you can get the waves not completely lined up. And so you get this process where sometimes they add up to being twice as much, and sometimes they completely cancel out. And that process mathematically can be put together to figure out exactly, much more accurately, for example, where the source is. And if you use multiple antennas, you can end up essentially making images in radio waves, something you can't easily do without this technique. And so Ruby Payne Scott developed the mathematics behind this, and it is what powers, for example, the Australia telescope up near Narrabri, and those mathematics are the foundations for which the Nobel Prize in interferometry was given. I think in a modern era, I would honestly believe that if the Nobel Prize were given today, she would have been one of the recipients. She, unfortunately, or fortunately, as I'll explain, became pregnant in 1951, not very long after she did all this seminal work. And she worked for CSIR, and like every other institution in the country then, women, when they were married, were not allowed to work. It turns out she kept her marriage secret, but when she became 6 months pregnant, it was rather difficult to keep that secret, and she was dismissed with a fair bit of huff about bringing CSIR into disrepute, effectively. And that was the end of her career. The amazing thing is in the children that she reared, which include Australia's probably most renowned statistician, Peter Hall, who's now at the University of Melbourne, and Fiona Hall, the well-known artist, who you will go out if you see at the Botanic Gardens, some of her stuff is there. So she did well despite the obstacles against her. So we're going to go back now from that segue about telescopes and look at how telescopes changed the world, our view of the world. So the first big telescopes here were odd structures that allowed people to go out and to start looking fainter than humans had ever been able to see. And so when the sky was being looked at with these telescopes, a new planet was happened on. And this planet was Uranus. Now, it was seen to move across the sky as planets do. And planets move across the sky partially because they move around the sun, but mainly because the Earth moves around the sun and it gets a different perspective on the planet as it looks far away. That's not something that's necessarily obvious to most people. But as Uranus was seen to be moved around, it was realized to be an orb, and so for the first time in human history, a new planet was discovered. The other ones had been known forever, for all of eternity. And so the telescope showed us our first new planet in history because it could see fainter than anyone had seen before. One of the interesting things about this planet is they watched it go around the sun. They applied Newton's laws to the planet's motion, and they realized the planet wasn't quite going where Newton's laws of gravity said it should. What did that mean? Newton's laws were wrong? Possibly. But then someone had an idea. They said, you know, I could fix this with Newton's laws being right. All I have to do is add a new planet. And that new planet, now known as Neptune, was essentially predicted to exist. And in a case of some interesting French-German cooperation, which probably hadn't been seen for hundreds of years before or after, in 1850 approximately, Leverrier predicted this planet should exist, and Gottfried Galle in Berlin found it. But it was an idea. It didn't have to be true. The reason we know it's true is because we were able to go out and see this new planet. That's how ideas work. If the planet had not been there, then Newton's laws would have been the thing that we would have had to change. Now, technology moved slowly, and in the 1930s we were able to take pictures of the sky with big photographic plates. And Clyde Tombaugh did this in the 1930s, and here on a tiny little smudge you can see Pluto, the once planet, the 9th planet, wandering across the sky. He looked at essentially every part of the sky he could see from the northern hemisphere. And it was that new technology that allowed that planet to be discovered. But it was even newer technology that took it away, and it was through digital detectors that were 100 times more effective than these photographic plates. And here I show you a planet moving. It's this little guy right here. Let's try that again. That is Eris, E-R-I-S, an object further away but bigger than Pluto. This led us astronomers to try to figure out what to do. And so at the International Astronomical Union meeting in Prague, we all got together and had to make a decision. What is a planet? I voted that once a planet, always a planet. I was outvoted, it turns out. Other people decided planets were something else, which I don't completely understand the definition. I still feel right about this, but Pluto, rather than having a sibling added in the form of Eris, was demoted to become a dwarf planet. But ultimately, planets are what we say they are. There's not a real honest-to-God definition. So, once again, we see new technology reinvigorating the field. Pluto is not alone, and indeed, when we go out and we look further, we have found all sorts of interesting things wandering in the outer solar system. Eris is the largest, Pluto very close. We now know Pluto has 6 moons. And then a whole lots of other interesting objects out there, all probably formed from sort of the flotsam and jetsam left over from when the solar system was formed. That is one of the reasons why we didn't really like Pluto to be a planet. It sort of was an afterthought. Now, one of the big fields of research right now is discovering planets around other stars, and we can do this very effectively. So the way we can do this is, there's several ways to do this. One way is to take the light of objects and spread them out into spectra or into the colors of the rainbow. And when we do that, for example, for a star, every atom has a fingerprint of light where it either emits or absorbs light. And so you can, for example, tell what's in the sun based on this fingerprint of colors. Helium was discovered in the sun before it was discovered on Earth from its fingerprint. It was only later that we realized that helium, named after the Greek god of Helios, was here on Earth. So it's a very powerful technique. And so you can go through and essentially at a distance see what anything's made of that you can get a spectrum. Now, we have the effect of what we call the Doppler shift, which affects waves. So we know it from sound. For example, if a police car goes by you or an ambulance goes by you with its siren on, the pitch changes due to this effect of essentially moving relative to the speed of sound or light. The pitch or color is changed. And so we can use this effect to gauge how fast an object is moving. And so, for example, if an object is moving towards you, its light is compressed a little bit, which makes it bluer. And if it's moving away, it's stretched a little bit, it's made redder. And so with modern instruments, we can make amazingly precise measurements in this space. And so, for example, if you have a planet orbiting a distant star, we know, for example, that the Earth orbits the Sun, but we also know that for every action, there's an equal and opposite reaction. And so as the Earth makes its 365-day journey around the Sun is making a tiny little journey itself around a little circle very near where it, in the center of the solar system. And that motion of the Sun, which you can pick up with the shifting spectra, allows us to measure the presence of planets from this little circles they do. The amazing thing to me is how accurately we can make those measurements. It is routinely made to the level of 1 meter per second. We can measure something, thousands upon thousands of light years to 1 meter per second. And so 1 meter per second is about like this. So I can measure a star, which is 1,000,000 times bigger than the Earth's motion, at this rate. And that turns out to be good enough to find a lot of interesting things. And it turns out that the bigger the planet, the faster the star has to move in a circle to counteract the motion of the planet. So you can weigh things, you can figure out how far the objects are away, and it can be used at objects that are extremely far away. Now, a program has been on for the last 10 years at the Anglo-Australian Telescope. Here's the AAT on maybe not the best day for observing, the 13th of January this year, about 2 minutes before a bushfire overran the place. One of the great things about this day was that 9 years and 361 days earlier, Mount Stromlo had a similar day, except for we completely were destroyed. And that meant that we learned some lessons, and we applied those lessons to the site, and we did not lose any telescopes, despite an incredibly severe bushfire. That telescope has found many, and programs have found many planets. The most interesting is in a fairly, a star you can see with your eye, but they have discovered a whole set of planets, it appears, around this star, one of which is something that you could imagine being habitable by life, because it's bigger than the Earth, but it's not so big that we don't think it's made out of rocks, and it's at a distance such that water is neither frozen or evaporated. This is an object that is less than 7 light years in distance. It's one of the nearest stars to us. And so this is a very exciting discovery done here in Australia using the AAT. And so who knows, this is sort of what an artist's conception of what this solar system might look like. But at some point, if humanity, in whatever form it will be in the future, wants to survive, our sun will die, and maybe this isn't a bad place to check things out, see what's there. Australia was founded on the second technique that we use to discover planets. James Cook, to what I would describe as a slightly ironic set of conditions compared to the way things are now, was commissioned by the Royal Society to go out and measure the transit of Venus. So when Venus goes in front of the sun, it turns out you can use this by doing this at 2 places on Earth simultaneously to measure the distance to the sun very accurately. Because scientists were so rich in 1766, 67, and the military was so poor, the military said, while you're there, could you do a couple things for us? Like, go look at this land called Australia. And so he got his orders to go do that via the military, but paid for by the science. I promise you that doesn't happen anymore, where the military takes free rides on the scientists. We are known for doing it the other way occasionally. So I don't know how many people got to see the transit of Venus last year, or the one in 2004, but the idea is Venus goes across the sun and blocks out a little bit of its light for a few hours. Now imagine the sun was not right next door, but rather was, on the other side of the galaxy. The same process occurs. The same amount of light is subtracted, in this case about 1 part in 10,000. And this is a really interesting way to find objects as well, because our instruments are so good we can make really precise measurements. So here in Australia, I'm part of a program called HAT-South. It includes people in Europe and Chile and in the United States, where you go through and you look at hundreds of thousands of stars and you track how bright those stars are over time. Now, we've been going, and this is a fairly exciting day at this telescope on the 13th of January. This is an image taken as the fire front went through. I have to admit, I didn't think we were going to have a telescope after this, but it all survived, amazingly enough. But you also find things like this. So this telescope is just beginning to find lots of planets. This is our first one. And you can see a little thing passed in front, and that little dip is a transit, not of an object like Venus, an object much bigger than Venus. But our hope is that these planets are kind of weird, we don't understand them, and by finding lots of them, we can understand how solar systems are created. And so this is a nice little program here in Australia, but there's also been quite a remarkable program using a spaceborne probe where you can do much more fine measurements. That has been getting a lot of attention recently. Kepler, because its reaction wheel, a little gyroscope that keeps it steady in space, has failed. And so this telescope has done everything it was designed to do, but it was doing it so well, we wanted it to do a bit more. So this telescope is sensitive to objects as small as the Earth, so it can find objects like the Earth transiting in front of stars, and indeed it seems to have found quite a number of things in that regime. And so here are just some of the objects it saw, and one of the most interesting ones, one of the first ones, was what we call a super-Earth, a star that has a planet probably twice or 3 times as big as the Earth. We still think it should be made out of rocks, but again, contained in that habitable zone, kind of on the warm side of the habitable zone. But a big planet, it's going to be really good at retaining its atmosphere compared to a small planet. So again, this one is a long ways away. We're probably not going to hop in a rocket ship anytime soon. Our current rockets would take us about 250,000 years to get to the really nearest star. This one would take much, much longer. But Kepler has shown that almost every single object, every single star in the solar system has a planet. Now, I can't say they all do, but on average, there's a planet per star and probably more than one. Right now, we have a catalog of planets, and this is a slide I made, I think 4 months ago, 677 planets. This is the one I made today, 908 planets. Kepler has been responsible for lots of those. It has been an amazing time to really, for the first time, stake out what is happening with planets around the universe, or at least our own galaxy. One of the other new things that we're going to be able to do in the soon is to use those adaptive optics to go through and make really good images and see the planets directly. With the 8-meter telescopes, for example, Gemini, shown here, you can see these 2 planets in light that they reflect off their sun. So we're just able to do that now. But the future is much more exciting. Here is a picture of Venus when it transited in front of the sun. This is not Photoshopped. This is a picture taken from a satellite that studies the sun. And I want you to look at it. Up here, there's this little beautiful ring of light. That is light that has been refracted through the atmosphere of Venus. And so that light has traveled through Venus's atmosphere. When light travels through atmosphere, the fingerprints of whatever's in the atmosphere are put into the light. So you can go through when planets do things like this and see what their atmospheres are made out of. We have the prospects of going through and seeing whether or not, for example, there are planets in the habitable zone that are full of oxygen, which we think is a calling card for life, because oxygen cannot be in the atmosphere on its own. It needs to be put there by something like life. And the telescopes that we're going to do this with are not the ones we have now, but the next generation of telescopes. Here is one that Australia is involved in, the Giant Magellan Telescope. It's made up of 7 mirrors rather than 1, and you can see how big it is. Those 7 mirrors are big compared to even this room. So probably getting close to the length of the room, certainly bigger than the width. And this telescope isn't going to be ready for 2022. It takes a long time, and it's a telescope that Australia is a 10% partner. We're working with a bunch of US institutions as well as Korea to build. So these types of telescopes allow you to go through and get enough light till you can start looking for the fingerprints of planets and see what they're made out of and start asking the question, how frequent is life in the universe? The other thing you can do with these big telescopes is look very far away. Now, the best telescope we have to do that right now is the Hubble Space Telescope, and here I'm going to zoom into a little piece of sky to the most distant picture taken in the universe to date. And if we zoom in further and further, we see a tiny piece of sky, a piece of sky that is 1/32 millionth of the entire sky. So with the Hubble Space Telescope, you take 32 million pictures like this, and you've taken a picture of the entire sky. This image contains 5,000 galaxies. These galaxies are like the Milky Way, which means they contain about 100 billion stars each. Each one of those stars has, on average, a planet, maybe a few more. So you can ask yourself, how many chances are there for life in the universe? And the answer is a lot. There's 32 million pictures like that one. Each one has 5,000 galaxies. That's 160 billion galaxies in the visible universe where we can see. Then you go through and say, well, each one of those galaxies has 100 billion stars. And you multiply that out, and that's a lot of stars. So I was trying to think of, gosh, what's the biggest number I can relate to? Couldn't really come up with something, so I'll do my best. So I said, well, how many grains of sand are on the planet Earth? And so I looked it up, and the number I got was that, or maybe 3 zeros less than that. It turns out the number of grains of sand on planet Earth is less well known than the number of planets in the visible universe. There's some irony to that. But there are more chances and more planets in the visible universe than there are grains of sand, right? Probably a factor of 1,000 to 1,000,000. So I don't know if there's life out there, but I can tell you there's a lot of chances for it. So this begs the question, okay, lots of chances for life. How did this all get going? What's going on here? Well, let's look at what how the universe changes, the area that I study of cosmology. So 13.7 billion years ago, 13.8 billion years ago, give or take 100 million years between friends, we don't care too much in astronomy. Those are small numbers. The universe, for some reason, turned on. We call that the Big Bang. I don't know what came before the Big Bang. I don't even know what the Big Bang is. All what I know is that the universe turned on at this time because we can see back literally to a few minutes after this time using various techniques available to us. Now, I don't have time to go through those in excruciating detail, but one of the things we do know is that if the universe was really hot and really dense, then through quantum mechanical effects, you can literally have matter being created and destroyed within space itself. And so when the universe was maybe 1,000th of a second old, we had protons and electrons and neutrons literally being created and destroyed just in space. Matter was everywhere. And the reason it could be created and destroyed is because of Einstein's E equals mc squared. You can convert energy into matter and matter into energy. And quantum mechanics allows that to happen when there's energy available. You can, mysteriously make something if you do it for a very short period of time. So that whole process was going on. And then the universe cooled down a little bit because things, when they expand, cool. And so as the universe got bigger, the universe is expanding at this time, and I'll show that in a little bit, why we think it's expanding. But just accept for a moment that it does that. The universe will cool down, and when it reaches a temperature of about 800 million degrees, it's very similar to the temperature inside of our sun. It's made out of hydrogen, it's lots of stuff. It's a giant nuclear reactor, just like our sun. And the physics of nuclear reactors, thanks to the Cold War, are very well understood. And so you can go through and you can calculate, if the universe was created in a Big Bang, how this nuclear reactor would work. And that nuclear reactor says, well, at the very beginning, there would have been protons, but this nuclear reactor would have taken protons and the neutrons, crammed them together to make something called deuterium, also known as heavy hydrogen. Whenever you see the World War II movies with people going up to Norway to blow up the dam, which makes heavy water, well, it's because deuterium was the hydrogen in that water. Why? Because deuterium turns out to be nuclear, is a very easy thing to cram together and make helium. And when you do that, you get a nuclear reaction. And here on Earth, you get energy, and it's a good way to, for example, to make a large bomb. We haven't figured out, unfortunately, how to make much power this way without putting more power in than we make. It's almost break even. So this nuclear reactor goes through and ends up in the first, 200 seconds of the universe, makes a quarter of everything in the universe into helium. And that is something that you can calculate very precisely. So Big Bang created a universe with 3 parts hydrogen, 1 part helium, tiny amounts of some other things, for example, deuterium, lithium, but nothing else. So as the universe now has, after 200 seconds, it continues to expand, it cools. And as it cools, at some point, it looks like this. It makes this transition at 380,000 years old, it turns out. The universe has cooled not to be 800 million degrees, but rather 4,000 degrees. And at 4,000 degrees, something interesting happens. Electrons, which are, we always think of as being part of an atom, well, when atoms are hotter, or hydrogen atoms are hotter than 4,000 degrees, the electron is not attached to the proton. And we call that, the atom is said to be ionized. This is important because if you have an electron all on its own, it looks like a giant cricket bat to a photon. So you may think that a proton, which is a little bit more than 1,800 times bigger than an electron, would look like a bigger target to a piece of light. And that is certainly not the case. Rather, it looks like this. The electron looks like this huge thing when it's not with the hydrogen atom. And so you have a universe that's very hot. It's full of electrons that are off on its side, on their own. And the protons we don't care too much about because the light basically doesn't see them at all. And so as the light tries to travel through the universe looks a mess. It looks like that. It looks like a bunch of cricket bats, and the photons get whacked around as they try to bounce around the universe. Now, if I suddenly filled this hall full of electrons, it would probably kill us, but we wouldn't be able to see through it because the photons would be bouncing. They wouldn't be able to come straight between you and me. It would be like a fog was in this room. So the universe was essentially full with a fog of electrons before it cooled below 4,000 degrees. When it cooled below 4,000 degrees, the hydrogen atom suddenly grabbed the electrons, and the universe became transparent. So this gives us, it's like taking a snapshot of the universe. It's been handed to us. It's fog, things are moving around, and suddenly the veil is lifted and you see the universe exposed, just as it was at 380,000 years after the Big Bang. That's remarkable because the physics of what's going on there is complicated but understandable to us because it's not dissimilar to the conditions we can create here on Earth. And so that gives us a great opportunity to study what's going on in the universe. And it turns out the study of what are effectively sound waves in this image allows us to figure out what the universe was doing very precisely. Now, the universe continues to cool, and nothing really happens in the universe. But those bumps and wiggles are being attracted by gravity, and over about 100 million years, gravity collapses those sound waves, those bumps and wiggles, starts forming the first stars and galaxies. That is an area of the universe that we are right now trying to understand for the first time. How are we going to do it? Well, one way to do it is to try to look at hydrogen when it's cool but isn't in stars. Now, hydrogen that's cool and not in stars doesn't emit much light, but it does emit radio waves, which of course is a form of light. It turns out a proton and electron both have spins, and that if you somehow have the hydrogen atom made of the proton and electron, nice cool state, the spins can flip, and when that happens, a radio wave comes out. And so we can use radio telescopes to look at cool hydrogen. The problem is this stuff is a long ways away, and it's very, very hard to see. And so in Western Australia, we are at the beginnings of building a huge radio telescope to go through and look at this cool hydrogen left over from the Big Bang as it starts to form the first stars and galaxies. Just a couple days ago in Melbourne, we launched with the science minister the first regular observations from this telescope called the Murchison Wide Field Array. You can see it's out in the Western Australia desert, and here is a bunch of, not a very exciting looking telescope, but a very effective one. It's a telescope that's really a computer. And using computers, you can combine the signals from all these things that look like, I don't know, a bunch of coat hangers, and make a signal of what the radio waves are coming from the distant universe. Now, this is a very challenging experiment. It's not clear it will find things, but it is what we call a precursor or a prototype to the Square Kilometre Array, a huge telescope that has people from around the world helping Australia to build. The other telescope that is out at Murchison is one that looks maybe a little more familiar. This is called the Australia Square Kilometre Array Pathfinder, ASCAP, being built by CSIRO. And so this takes a bunch of dishes and is able to look at cool hydrogen, not on the other side of the universe, but much more locally. So we can see the cool hydrogen and study galaxies nearby and see how things have changed through the fullness of time. We hope in the next 10 years, finances willing, that we are going to have a huge spread of these across the Murchison Shire in Western Australia, and hopefully we'll end up with a square kilometre, that's a kilometre by kilometre of collecting area, so that we can go through and study that early universe, and probably do some pretty interesting telecommunication stuff and digital processing along the way. So Australia is, with Southern Africa, hosting the Square Kilometre Array, and we will be watching this be rolled out over the next 10 years. Another way, which I like to go through and study the early universe, is more akin to archaeology. Here is our Milky Way galaxy. This is a picture, if you go through and take from space in the infrared and you just look at all the stars, that's what our galaxy looks like. 100 billion stars in there. And some of the stars will be the fossil remnants from when the Milky Way was formed. These stars won't have anything like iron in them, because remember, there was no iron formed in the Big Bang. So using a telescope which can go through and look at the entire southern sky, we are going through and searching for stars that are like this one. So here is a picture of the sky, and we're going to zoom in, possibly. Yes? Nice and slow. So to give you a scale of what it's like to go through and find, one star in 100 million, I take you into a random piece of sky. We zoom in, zoom in, zoom in, and that boring-looking little star right there turns out to be the object in the sky that has the least amount of iron ever seen in a star. About 100,000 times less than our sun. I should say that was the previous record holder, because here in Australia, we have a new telescope that's going through and surveying the sky. So that's this star. And I can't show you a picture yet because the paper has been submitted to Nature, but SkyMapper up at Siding Springs has started surveying the sky, and it has discovered a star that has no detectable iron. None. Now, we can't say it has 0 because we have to be able to make a measurement. But we know that it is less than 10 million times the sun. So a truly remarkable object. For the astronomers in the audience, it does have some other things in it. So we know it isn't one of the first stars left over the Big Bang. But it is certainly a star that formed right after the Big Bang from probably one of the first stars. And so this telescope is a new breed of telescopes that can look at a piece of sky about 40 times bigger than the full moon. It has Australia's largest digital camera, at least unclassified digital camera, 268 million pixels. And over the course of the next 5 years, it will take about a petabyte of data. So a petabyte is 1,000 terabytes. A terabyte is 1,000 gigabytes. And I think most of us know what gigabytes are now. That seems like a lot of data, and it sure was 10 years ago, but it's actually not that much data anymore. It's, I won't say it's easy to get through, but it's not nearly as hard as it used to be. So imagine you can go through and figure out the fingerprints of chemistry of every star, or lots of stars, in the Milky Way. Well, SkyMapper, it turns out, can go through and give you a first coal. And then our other big telescope, the Anglo-Australian telescope I showed you earlier, is equipped with a unique spectrograph, something that takes the light and puts it out into the colors of the rainbow, which can look at many hundreds of stars at a time. And so we are hoping over the next couple years to commission this new instrument, and we are literally going to do the chemical fingerprints of 1 million stars. And in that way, it's sort of like doing the DNA of 1 million people and trying to figure out how humanity evolved. We can literally use this DNA fingerprint to figure out how the galaxy evolved from the chemistry over time. Because each star has its own unique chemistry based on essentially its parent stars. Very similar to how we deal with DNA in humans. So one of the great things that we can do with these big modern new telescopes is try to reconstruct the future and the past of the universe from our observations. Now here in Australia, we got an early start on this thanks to the Parkes radio telescope. Parkes was one of the first big radio telescopes that was fully steerable, and it was able to do many breakthroughs in the 1960s, much to the jealousy of some of our international companions. One of the things they were able to do was to be clever. They could see, they knew that there was these very bright radio sources. They didn't know what they were. But the guys here in Australia waited for the moon to travel through this field, and suddenly the moon turned the quasar off because the moon went in front of it. And that allowed them to discover the exact position of the object, and that enabled optical telescopes, which certainly back then you were more able to, had better sensitivity, but also allowed you to pinpoint things, to go through and figure out what one of these were. And here was the image that was taken, Caltech, with the Palomar telescope, the largest optical telescope of the time, and there was a star, but it had this little thing sticking out of it. It was a bit of a mystery. It had a spectrum that was very funny, and it was eventually realized by a man by the name of Martin Schmidt, not related to me, that this was an object that was an incredibly long distance away, yet bright enough to be seen in binoculars. What could it be? Well, we're pretty sure now that these things are supermassive black holes. They are black holes 1 billion times bigger than our sun, or more massive than our sun. Sounds too crazy to be true? Well, we get more and more evidence. We now think we have about 1 million solar mass black hole just next door in the center of our own galaxy. And we can literally see the stars go around this thing and be sped up, and we can weigh it. And really, the only thing it can be at this point is a black hole, because we know it's very, very small. In 2001, in the optical, using the Anglo-Australian telescope, which was built because our radio astronomers were so frustrated that they were able to do all this great work with Parkes, but kept on being scooped by the Americans who had the optical telescopes, that they decided they needed their own. And so the Anglo-Australian telescope was a joint project between Australia and the UK, and it is the workhorse facility for Australia even to this day. In 2001, they went through and they mapped out the nearby universe with this instrument that I told you can look at 400 things at a time. Well, it can look at stars, but it can also look at galaxies. And what it was able to do was to measure the galaxies of the local neighborhood and essentially map out where they were in the sky. And you can see that galaxies form a foam structure. That foam structure is due to the fact that galaxies are formed by gravity. And so if you go through and you start with that sound wave structure, I showed you the map of the universe right after it was born, and you run it forward, you can actually weigh the universe very accurately by how foamy this structure appears. So the guys in here in Australia using this technique made the first really accurate measurement of the total mass or gravitational pull of stuff in the universe. The other thing, and so it turned out that the number they got was interesting because it indicated that for every piece of gravity we saw, there was only a fifth of the number of atoms that could be accounted for. In other words, for every atom, there was 5 times more gravity could be accounted for. Now, one of the things that I did is I went through and measured distances using how bright things appear. By looking at how bright something appears, the further away it is, the fainter it appears, I was able to go back and trace back what the universe had done in the past in a way very similar to what Hubble did. So Hubble, in 1929, discovered that the further away an object was, the faster it was moving away from us. So in a cartoon, essentially what he saw was the following. You take the universe and you expand it, and when you overlay the first image and the second image, you see that nearby objects, when the universe is expanding, move a little bit, and the distant objects, they move a lot. And so if the universe is expanding, you're going to see the further away something is, the faster it's moving. And it doesn't matter where you are in the universe, you see the same thing. So when I came here to Australia at the end of 1994, I had this new instrumentation that was coming online in the form of digital detectors, but I also had a new idea to use the brightest stars that we had available, exploding stars known as supernovae. And I could use them to measure distances. And instead of doing what Hubble did, which is just to measure things nearby, I could look back into the past by looking very, very far away. And I could therefore see how fast the universe is expanding now and compare it to what it was doing billions upon billions of years ago. And so this is, as part of the school, I gave a full talk, about an hour, on this whole thing. So we're just going to get straight to the chase today, since several of those people are here. But effectively, this is the experiment we did in 1998. Each supernova, or exploding star we measure, allows us to measure how fast the universe is expanding at how long it's taken for that light to get to us. So nearby objects, for example, these, you can measure how fast the universe is expanding. And you can see there's sort of an average there. Each one has uncertainty, and that uncertainty is given by this error bar. That means 2/3 of the time the answer will be in that error bar, and 1/3 of the time it will lie outside. So you sort of have to do an average with your eye. Now, when we made this measurement in 1998, we looked at the distant objects, and what we saw was that on average, those objects were saying that the universe was expanding slower in the past and had sped up over the last 5 or 6 billion years. Now, that didn't make any sense at all, because what would make the universe speed up? We know the universe is full of gravity. Gravity pulls on things. When you pull on things, you slow them down. If I throw a ball up in this room, the ball will be pulled down by gravity. It would not speed up. So I have to admit to thinking when we first saw this, that we had made a mistake. But through careful effort amongst our whole team, it became very clear that we didn't. So in 1998, we announced our results. Turns out a competing team out of Berkeley found the same thing using the same technique at the same time, independently. And so it wasn't a fluke. It really was what the world was doing. And that is for the work that we received the Nobel Prize for in 2011. And to give you a sense of what it's like to win a Nobel Prize, since I'm sure many of you want to know this for when you win yours, something I would have liked to know when I won mine, is that when you arrive in Sweden, they genuinely do treat you like royalty. You don't have to get off the plane with everyone else. Rather, they meet you at the gate with a chauffeur and a BMW, not a Volvo. They give you a driver. The driver, in my case, says, "Hello, my name is Stig." And I said, "Stig? Okay." So Stig got us around the streets of Stockholm very quickly. Since you're being treated like royalty, of course, you meet the royalty. In my case, the king gives you your award, and they rent you a princess for the evening. And all in all, they treat you in a way which is amazing. Science has a huge debt to pay Swedish society. This is their big event, and they put it towards science and something that the world can share and hopefully enthuse people around the world about the science we do. So here's the team that did the work behind that Nobel Prize. Science is not done typically by lone wolves anymore. It's done by collections of people who work together. And so the 20 of us, this is the first and only time we were all together at once. We all knew each other, we had all seen each other, but we had never been in the same place at the same time all at once. And that's the beauty and the curse of the internet, because we worked via email and things to do things. But it does show you how working collaboratively is possible these days. So one of the questions people asked before we won the Nobel Prize is, are we right? Well, lots of work went in to test it, and everyone kept on getting the same crazy answer we did. But now we want to know not whether or not it's actually happening, but exactly what is happening. And here in Australia, they have been able to do a very innovative experiment, again with the Anglo-Australian telescope, where they go through and they measure the sound waves, not back right after the Big Bang, but it turns out those sound waves eventually turn into galaxies. And so you can see those sound waves nowadays in how big galaxies appear. So they have done recently a huge map, and Chris Blake, who's at Swinburne, has helped lead this stuff. And this team here in Australia has managed to make some of the most impressive measurements of how the universe is traveling over time. And I'm very happy to say that they've effectively got the same answer that we've gotten with supernovae, showing that we both are getting the same answer, that the universe is speeding up, doesn't seem to ever want to stop, and it's speeding up in a way that turns out was predicted by Einstein in 1917, but a prediction that Einstein later described as one of the greatest mistakes of his life. So the plan, what we seem to have in our universe is a very messy universe, of which only 5% of the universe are the atoms that we're made out of. 95% of the universe is in the form of stuff that we cannot see. Dark matter, the stuff that's has gravity that's not atoms, and dark energy, the stuff that Einstein invented that pushes the universe apart. Now, if we have to invent 95% of the universe, you may well think we don't know what we're doing. That would be a perfectly reasonable conclusion, except we have literally done hundreds of experiments where this model has been able to pre-predict what we have observed. And that comes down to the ideas that I started with. What is reality? Reality is an idea that predicts things. This is the simplest idea that we have that predicts things. Does it mean it's right? No. But we will never know what is right or wrong, because nothing is right or wrong in science. It is always the hypothesis that we use today. So dark matter. What is dark matter? It'd be great to figure out what dark matter is. We suspect it's some undiscovered particle. If dark matter is some undiscovered particle, there's a very reasonable chance we will discover it in the next 10 years. Not guaranteed, but a very reasonable chance. Neutrinos are a particle we know. They go right through our body right now. They can go right through the Earth. They're weakly interacting. They're well named. There could be another particle we haven't yet discovered that has that same property. It'll go right through the Earth. And we only know things exist by when they interact. This particle would seem to only interact by gravity. And since if it only interacts by gravity, it's extraordinarily difficult to detect by anything other than gravity. We might be able to create it within the Large Hadron Collider, or we might be able to detect it interacting with atoms when it very rarely occurs, and we have big hunks of germanium and things, or xenon, miles below the surface of the Earth, waiting for a collision to occur, which we, right now, doesn't seem to happen frequently enough for us to detect. So that is part of the story, but still a mystery. Dark energy, the stuff that we seem to have discovered with the accelerating universe, is a far bigger mystery. We don't really even have a good idea what this stuff is. We know it has to be energy that is part of the fabric of space itself. That is the way Einstein invented it, to make it push rather than pull. But why would space have energy? That is one of the big mysteries of astronomy today. But we do know that the future of the universe seems to be this dark energy, because this stuff makes gravity push rather than pull. It is part of the fabric of space itself. So as space expands, this stuff gets created in the expansion of space. The stuff that has gravity, atoms, dark matter, it doesn't get created. And so the stuff that has gravity that pulls gets diluted over time. The more the universe expands, the faster it can expand, because the harder this stuff can push, making the universe expand even faster, but even bigger, meaning this stuff can push even harder. You get a runaway effect, or exponential growth, not dissimilar to inflation for the economists in the audience. So this is remarkable in that eventually space can be expanding so quickly that light cannot reach things that you can already see. So, for example, if I look at a galaxy, the galaxy will be so much space will be created between us and the galaxy that its light will get stranded on the way to see us. Meaning that effectively things we see right now in the future will no longer be visible. The universe is effectively, although it's getting bigger, the amount of stuff in it is getting smaller and smaller over time. Doesn't mean that stuff doesn't no longer exist, it just means we can't see it anymore because light from it can never reach us. So in the future, this part of the universe is not expanding because it's really dense here. Atoms are able to collapse and cool and form things like the Earth. There is 30 orders of magnitude more atoms in this room than there is dark energy. So our part of the universe, dark matter and atoms won the battle of the universe, where we were able to overcome the expansion and bring stuff back down and form Earth. It turns out the Andromeda galaxy, the largest nearby galaxy, is also within our gravitational well, where we have more gravity pulling than dark energy can push. So in the not too distant future, about 3.5 billion years, the Andromeda galaxy and our Milky Way will merge together in a very fantastic display. Don't worry, no planets will be harmed in this, because space is very vast and there's huge amounts of empty space between the stars. But we will end up living in a very boring galaxy full of stars. But the galaxies beyond Andromeda, well, they will get further and further away because they are outside of our gravitational pull, and we will look onto an empty universe beyond our own stars. So this is a rather perverse end to the universe. In the future, assuming this dark energy doesn't suddenly disappear, the universe will continue to expand at an ever-increasing rate and slowly fade away from our view, leaving cosmologists like myself with nothing to do. So please fund my research now. Thank you very much. Not too long, sorry.
Thank you very much, Brian. Now, we do have some time for questions, and you're able to roam, but I'm tethered here. And if I could ask everyone who would like to ask Professor Schmidt a question, please avail yourself of the 2 microphones that we have down the central aisle here. Make an orderly queue, and we already have a gentleman at the front microphone, so you may kick us off, sir. Please do ask a question.
Thank you. Do neutrinos have gravity?
Yes. They don't have much because they're very, very light. So a neutrino, we don't quite know how much a neutrino weighs yet, but neutrinos are very, very light. They're much, much less than an electron by a factor of 1,000 or so, at least. But even light has gravity. Light has energy. Energy is equal to mass in general relativity, and so everything that you can think of has gravity.
Was it considered for a while that the neutrino was a candidate for dark matter?
It was a long time ago, and
so I'm
there
way
are
behind,
even
okay.
some ideas that there might be some funny types of neutrinos that might well be dark matter. We're working through those because those make things we can test. As of yet, haven't been able to figure it out.
Okay, we'll jump through to the back microphone now.
Me?
Yes?
Good evening. This is an old question. Is it possible that the universe, instead of being in spherical shape, unlimited 43 billion million years, as this morning in the radio was broadcasted, is it possible that it would have a shape of whirlpool, spring, that it wouldn't be extended, but it would be twisted within and around itself? So the space between point A and B would remain the same, 42 billion light years, but it is actually far closer physically than being far, far, far away.
So the question of
So the question
seems to be around the structure of the universe.
So we can test a lot, and so if the universe had the shape of a whirlpool, for example, which is I think you were asking, it should imprint itself a bit on that cosmic microwave background, that imprint we see of the Big Bang, because we can see that all around. If it were a subtle effect, perhaps it could evade detection. The question, though, is that we think the universe could easily have the shape of a sphere or even a donut. What we know is any such shape is much larger than the part of the universe we see right now. So if the universe has a real distinct shape, it's much bigger than what we can see. And so it's very hard to know that it has that shape.
Energy. Thank you.
Isn't it fascinating to think that, that's a testable idea? That you can ask a question, is the universe round or donut-shaped or whirlpool, and you could actually
You can
test
start doing it, but of course, if you're the tiny little, imagine the donut is huge, and we're a tiny little postage stamp, the part of the universe we can see, on that huge donut, then unfortunately it's sort of like why people think the Earth is flat. It looks flat here because the curvature is so big you can't see it.
Tiny little sprinkle on the donut. Of
That's
the universe.
correct.
That's poetic, almost. Let's go to the front microphone again now.
The questions on the total energy in the universe.
Yep.
Two things I've heard. First, that the energy, matter and light exactly balances negative gravitational energy, so the totality is zero. The second one is, as the universe expands, light is losing energy through its expansion. I've heard that there's a calculation that shows the amount of dark energy coming in exactly balances that. Is that true? And the thing
That
I
second
don't-
one is pretty surely not true. The first one is, yes, if we try to, it turns out to be very difficult to absolutely measure how much the total energy of the universe is. It does appear to potentially be effectively zero. We can't rule that out, but I would still say there's considerable uncertainty in it. It turns, within general relativity, it's very difficult to define what the energy of the universe is.
Well,
Can I
if
just...
people think it is zero, then presumably in any large volume of space, they think it could be zero. So how can you have gravitational attraction on a universal scale?
Well, the idea is that when you look at the universe through Einstein's equations, you have all sorts of things that add to energy. The things that add to energy are how fast the universe is expanding or slowing down. It's what's in the universe. It's how the energy of those things like light, but also dark energy is changing over time. And it's the curvature of the universe. So it's quite a lot, a very complicated accounting book. And so you can trade those things off. That's what Einstein's equations do, but they are very complicated, and they did take them 8.5 years to figure out just the basic formulation of. So it's complicated, but as near as we can tell, it all holds together.
All right, back to the back microphone now.
You said the university became transparent when it was 380,000 years old. And before this, the universe created some helium and lithium and something else. But before the universe became transparent, what can we see? If we can see nothing, how can we know what the universe looked like?
Right, so we can't see any light from the universe after or before 380,000 years. But the sound waves contain information. So when we model the sound waves, the little ripples in the sky, we're actually looking back to how those sound waves have traveled for, a good part of the 380,000 years, probably about 379,000 of them. But before that, you can see the nuclear reactor. And so you don't directly see what the universe is doing, but you know what that nuclear reactor is doing very accurately. And so that tells you what the universe is doing. Before that, it becomes harder. We don't have any direct things. We know how the physics works because we can test that physics in the Large Hadron Collider, and that allows us to go to sort of a millionth of a second after the Big Bang, and then things become pretty hazy. There's a chance in the future there is something known as gravitational waves, and those have the potential to allow us to look back right to the time of the Big Bang. But we have yet to detect them. They are a theoretical idea, but we haven't seen them yet.
All right, we've got a question from a young gentleman at the front microphone here.
Do stars get picked up by other galaxies if other galaxies are passing them, or do stars have to be in a galaxy?
Yeah, so if we look at our own galaxy, it turns out the Milky Way has chewed up several other little galaxies. And when it does that, some of the stars get incorporated into the Milky Way, so they become part of our galaxy. Some of them stay as part of the galaxy because that part of the galaxy itself becomes part of the Milky Way. And some of them sort of get strewn behind and left out and can actually get ejected from both galaxies. And those stars are sort of all off on their own without a galaxy. They're sort of in between the galaxies. So there are not very many stars that get thrown out, but some of them do.
Must be pretty lonely out there. All right, back to the back microphone now. We have time for just a couple more questions, unless I get a signal from the back that says that we can go a bit longer. We are due to finish up around about 7:30. We'll see how far we get. So let's go with the question from the back microphone.
Professor Schmidt, I really enjoyed your talk tonight, and congratulations on your Nobel Prize.
Thank you.
I want to ask you about dark energy. You mentioned we predict to be 73% dark energy, pushing the universe away, and yet when we measured it, it's found to be almost zero. Could this be an indication that that value is just for this universe and that there are a number of other universes? And that relates to the other part of the question, which is, what is your position on the multiverse?
All right, so I think what I'm understanding is that if we think the value of the cosmological constant from theory should be very, very big compared to the measurement that we've made. Is that what you said?
Yeah, it's been described as a monumental mismatch.
Yeah, so one of the ideas about what dark energy would be is something that you expect from quantum field theory. And that is that in the universe, right here, right now in this room, you have, thanks to the Heisenberg uncertainty principle, bits of energy or particles coming in and out of existence for very short periods of time. That's allowed by quantum field theory. And so they don't last very long, so that, there's not a lot of energy there. But if you average everything up in the universe, then there's always a fair bit of energy in parts of space. It turns out a number about 120 orders of magnitude, that's a 1 with 120 zeros behind it, bigger than the measurement we have made. So that is one of the largest mistakes ever in a theory's prediction. It's a huge monumental mistake. So we don't really know what's going on there. One idea is that there's an infinite number of universes, and it turns out quantum field theory says, well, okay, the amount of these particles coming in and out of existence, that sort of depends. It's a probability of what you expect, and it's not very likely that you would have a universe where not much of this is going on, but it is possible if you have an infinite number of universes. Why would we be in such a universe? Well, because we exist. And if the universe had a lot more dark energy, we would have never been able to form and become humans in this universe to observe it. This is known as the anthropic principle. Do I believe it? Well, I can't say it's wrong. I don't think I learned too much about it. It pretty much is saying it's hopeless, we can't possibly know. So I think we're trying to look for a different explanation, but it also requires there to be an infinite number of universes. Now, I'm more than happy to entertain the idea of an infinite number of universes, but I would like to test the idea. And no one has really come up with an easy way that we can test the idea of multiverses. So
I believe that string theory supports the same line of reasoning, and eternal inflation.
Yes, so string theory and things known as eternal inflation are consistent with this idea. They're ideas, but remember, ideas become reality when you can see things. We haven't seen anything yet. So they're ideas. Some people believe in God. That's also an idea that I can't test. So you can choose your own.
Thank you very much.
Yeah.
All right, I think we might have time for one more question, and I'm sorry to everyone that we can't get a chance to speak to tonight.
I'm sorry I talked too long. That's a no-no.
But if we can have one last question from the front microphone, please.
Yes. Is it possible that there might be some other theory which could explain the observations without having to invoke the existence of this mysterious dark matter?
Dark matter and dark energy?
Well, and or dark energy. I've heard of something called modified Newtonian dynamics.
You're uncomfortable with the idea of only 5% of the universe being something we can explain? Well, surely. Seems quite reasonable.
So it turns out that modified Newtonian dynamics, this is where you're essentially saying general relativity breaks down sometime at some point when you're really, really far away from the source. So that's something we can go out and try to test. It turns out to be quite difficult to test, especially since the theories don't allow you to calculate things like we do in general relativity, because there isn't an underlying theory. It's essentially saying, well, let's just sort of add a little knob and turn off gravity selectively. So the difficulty is we can go out and we look at how the universe forms in that spongy structure. You would expect that modified Newtonian dynamics would affect that structure. So you need to be able to calculate what that structure looks like, and no one can really do it properly until you have a full theory. So it turns out to be harder to test than you might think. It turns out also it doesn't do much for dark energy. It doesn't do anything for dark energy. It really only gets rid of the dark matter problem, if you believe it at all. So ultimately, it comes down to a question. We have a thing of dark matter that seems to work well. The alternative theory we can't properly test. The other thing we can't do is make it work easily with the acoustic waves that are bouncing around the early universe. And so it's not a very good theory yet. If people can make it work, then we can test it. Then that's an idea we can try against dark matter, and we can choose the best one. So it really comes down to what is the simplest way to describe the observations we make. And at this point, the dark matter, dark energy scenario essentially can reproduce everything we observe with a, I won't say a simple, but a not too complicated model. And no one has come up with something that does better, or quite frankly, even close. So that's why we like this model so well.
It sounds like we're just going to have to get used to it. We're going to have to call it to an end there, I'm afraid. And as I said, I'm sure there are plenty of people who would like to have asked a question, but we are going to have to wrap it up for tonight. Now, when we invited Professor Schmidt to join us down here in Sydney for our International Science School, we were actually quite surprised when he accepted, because there are lots of demands on Brian's time. But I've only just realized today how many demands. And if he's not the hardest working person in Australian science, certainly today he's got to be the hardest working person in Australian science show business. Will you please help me in thanking Professor Brian Schmidt?
Thank you.